Hello everyone, welcome to Waves Lesson 3. This lesson is about sound. For this lesson you will need a pen or a pencil, a piece of paper or something to write on, and you can use a calculator if you want to. If you don't have these things, pause the video, go get them now. When you press play, we'll be ready to continue. We're going to start this lesson as we always do with a little mini test on stuff that you've done before. Have a go at these questions, pause the video, and when you press play again, we'll be ready to go through the answers. Let's see how you got on then. What is a longitudinal wave? A longitudinal wave is where the direction of vibration is parallel to the direction of the wave travel. For parallel, you could have said forwards and backwards, and for the direction of the wave, you could have said the direction of the energy or the disturbance. What's a transverse wave? Very similar answer to that, but the direction of vibration is perpendicular or at right angles to the direction of the wave travel or the direction of the energy or the direction of the disturbance. Frequency, that is the number of times the wave repeats or the number of cycles you get per second. The per second bit is very important there. What is wavelength? Wavelength is the distance between where a wave starts to repeat, or the distance between the peaks would also have been a perfectly correct answer. A cycle is one complete repeat of what a wave does. A period is the time taken to do one cycle. The wave equation is V equals F lambda, or you could have had velocity equals frequency times wavelength. You've got those all correct. Well done. We're going to listen to some sound waves now. I want you to look at them on the screen and notice what happens when. 1, the sound gets louder, the sound gets quieter, and 2, what happens when the sound gets a higher or a lower pitch. We're going to use an oscilloscope, which is basically a voltmeter that plots a graph of how big the wave is at any particular moment in time. So here are the things you should have noticed then. So look at these two diagrams here. So on the bottom one, the frequency, the pitch, that's how high it is higher because the peaks are closer together. So you can see here, these peaks here are very close together compared to much more spaced out on this one. You get more peaks per second. The amplitude, that's how loud it is the same. You can tell that because they both go up about 1.5 and down 1.5 squares. The same here, up and down 1.5 squares. Let's compare these two. On the bottom one, the sound is louder, and you can tell it's louder because the peaks go higher up. So from the middle there, these go up much higher than from the middle here, those there. So you can say the one on the bottom is louder because the peaks are taller. You'll notice the frequency is the same because the gaps between the waves is the same. So if you think this one goes 1, 2, 3, 4, 5, 6 peaks going across, 1, 2, 3, this one at the bottom is exactly the same. So the spacings is the same. The only difference is the waves are taller. Let's just see that video again so you can actually hear the differences. Try and remember those things because we've got some problems for you to have a go at now. All you've got to do is draw out the 5 boxes, and in each of the boxes you've got to draw a wave which is louder at the same frequency, quieter at the same frequency, same loudness, but a higher frequency, lower frequency, and then finally a little tricky, complicated one at the end, quieter and a lower frequency. So pause the video, have a go at those now. Let's see if you manage to get this right then. So louder, but at the same frequency, well, it would have been the same number of peaks going across, but the waves would have gone up taller. So the same number of peaks means it's the same frequency, but because it goes higher, it would make it louder. Quieter, again, same number of peaks going across, but it doesn't go up so high. Same loudness, higher frequency, well, the same loudness means the peaks would be the same height, but the higher frequency would have put more peaks going across. The same loudness and lower frequency would have been like that. Less peaks going across, but still the wave going to the same height. Quieter, but with a lower frequency, that means it's going to be not such a high peak, and also the wave peaks are going to be spread out more, something a little bit like that. If you got those right, well done. A new key idea for you to record now. For waves travelling at the same speed, as the frequency goes up, the wavelength goes down. Record that in your book because we're going to need that later on. Pause the video. Okay, time for a little experiment now. I would like you to copy this table into your books. Okay, let's have a go at the experiment. This experiment is we are going to try and measure the speed of sound. So I've enlisted the help of one of our science technicians, and she's going to measure out on the field 100 paces. Each of her paces is 85 centimetres, so she's going to be measuring out a distance of 85 metres. Here we go, heading down to the other end of the field, all the way down there. She's now 85 metres away. Now all she's going to do for this experiment is you can probably see she's got two wooden blocks in her hand. What she's going to do is she's going to bang the blocks together. Now when you see the blocks being hit together, that's when the sound is being made. When you hear the blocks, when you hear the sound of the blocks being hit together, that's when the sound is reached you. So if you start the stopwatch when you see it and stop the stopwatch when you hear it, then you've measured the time it's taken to travel that 85 metres. Let's see if we can give this a go. Let's turn the volume right up because it is quite quiet. Now, if you had your volume up, you may well have heard those sounds. Now, I wouldn't expect you to be able to use a stop clock and to record those times very accurately. Even if you were sat here with your phone timer watching the video, you would probably struggle a little bit. But through the magic of computers, I've managed to find the particular moments in time on the video clip on the video editor when they exactly happened. The top one, the top number is where you could actually see frame by frame the blocks going together, and on the bottom one where you can actually see frame by frame the little tiny sound mark on the sound bar at the bottom where the sound was received. So we know the exact times on the video when the sounds were produced and when the sounds made it to the video recorder making the video. So zoom in a little bit, you can see 2.094 is when it started, 2.376 is when it finished. So let's put those numbers in our table. You need to write them in your table now. You can see the time to travel from one end of the field to the other was 0.282 seconds. So if you've got them written down in your table, let's look at the next one, because she banged the blocks together several times. So on the second go, it started at 0.4612 seconds, ended at 4.885 seconds. So let's put those numbers into the table. Pause the video if you can't write them down that quickly. So there's our second set of readings, 0.243 seconds, quite similar to the first one. Let's look at our third set of results now. When we zoom in, it comes out 7.083 and it ends at 7.406. We'll bung those also into our table, and that gives us a time, a little bit high actually, that reading, 0.323, a little bit high compared to the last ones, but we'll live with it a second. These readings can go a little bit adrift, especially if it's a windy day like it was there, and sometimes the wind's blowing the wrong direction and can slow the sound down. Right, let's look at our fourth set of results then. Let's zoom in and see what they were. 9.657 seconds to 9.899 seconds. Bung them into the table there, and that gives us another reading, 0.242. That's pretty close. I'm quite happy with that. And the last one on here, zoom them in then, that was 12.021 and 12.272. So let's put those into our table. You'll need to make sure you've got them written down. So if you haven't been writing them down as we go, you'll need to pause the video now, and then you can make sure you've got a little bit of time to write them all down. And then in a minute, we're going to go on and do some calculations, see if we can work out the speed. So, little table here, distance, time, and speed. So the distance we know is 85 because that's what our technician measured out with our 85 paces. We know the times, that just came straight off the last table. So what we need to do is copy this down, and we need to work out the speed. Speed equals distance divided by time. So it's the distance here divided by the time. Distance of 85 divided by 0.282. Distance of 85 divided by 0.243, etc. So have a go at those calculations. Pause the video. Let's see what you should have got then. So these are the results that I calculated them at. 301, 350, 263, 353, 339. The actual value of the speed of sound in still air is about 343 meters per second. It can be a little bit faster or a little bit slower, depending on a number of things like the speed of the wind and the temperature. Obviously, the temperature, if it gets hotter or colder, will change the speed. Likewise, if it's blowing towards you or blowing away from you, that will change the speed. If you actually look, these numbers here are fairly close to 343. I'm happy that those results are fairly good results. So happy with that. We've measured our speed of sound to be very similar to the one that is the real scientifically known value. Another way of doing the experiment now, this time we're going to use the echo off the school building. So our technician is measuring out the distance. Coincidentally, she did 85 paces as well. She's measured the distance to the building being 85 paces. And what she's going to do this time is she's going to clap the blocks. We're going to hear when she starts the sound because we're right next to it. And we will also hear the echo coming back. So have a look at this. Oops. So you should have noticed that you get a bang, which is quite clear, and then you get a slightly muffled bang, which is the echo going back. Now we know the distance this time is not 85 paces, but it's double that because the sound's got to go there and back again. We can do a very similar thing with our stop clock, with our timer. We're only going to do one of these results just to show you how it would work this time. So the first sound was heard at 8.820 seconds. The echo was heard at 9.290 seconds, and we can put those into our table. This time the delay was 0.470 seconds. We put that into the table we've done just a minute ago. Of course, it's not now 85 the distance, it's now 170. The time is 0.470. This speed came out is 362. Bearing in mind the actual scientific speed, exact right temperature, exact right wind speed, well, no wind at all, would have been 343. We were pretty close, so I was quite happy with those results as well. That's how you measure the speed of sound. You can use this in everyday life. Let's say you're at home one evening and you've got a thunderstorm going on. So light travels so fast it takes as good as zero time to get to you. So when you see the lightning flash, that is when the sound was actually made, within a sort of billionth of a second or whatever. So when you see the flash, you start counting. Now, the sound of thunder travels at about 343 meters per second. Chances are, actually, in a thunderstorm, it'll be slightly different, because probably with a thunderstorm, it's going to be a little bit windy. What you do when you see the flash, you start counting. Every second you count before you hear the sound is about a quarter of a mile. So if you had lightning flash now, you go 1, 2, 3, 4, bang, 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 thunder. That's about 4 seconds, so the lightning was about a mile away. If you counted to 8, 2 miles, 6, mile and a half, something along that lines. As always, we're going to finish this lesson now with a little mini test. So have a go at these questions, pause the video, I'll go through the answers with you in a moment. Let's see what you should have put then. So 4 steps for an experiment to measure the speed of sound. So we're looking for 4 key points. Something about measuring the distance. You could have said, oh, you measure 100 meters, 85 meters, or whatever, or you measure the distance. Something about the method of doing it, the making of the sound, starting the stopwatch when you see them hit the things together, stop the stopwatch when you hear it, and then the calculation at the end, speed equals distance over time. Those would probably be the 4 things that I would be looking to measure. Draw 2 diagrams to show the difference between a low and a high frequency wave at the same volume. That's the same amplitude, but it would be these, wouldn't it? So they're the same amplitude, so they both go the same height compared to being flat down the middle. But the high frequency one, you'd probably need to label this one high, this one low. The high frequency one, the peaks would be closer together. Draw 2 diagrams to show the difference between a loud and quiet sound. That's a high and low amplitude sound at the same frequencies. The same frequency means you're going to have the same spacings between the peaks. We're going to get something like this. You can see across the little screen there, you've got 2 peaks there, 2 peaks there. So the spacings are the same, but the higher amplitude one is the one here on the left. Really, you should have labeled it, because it will be going up higher. The peaks go up higher than the low one. You got them right. Well done. Well, that's basically it for this lesson. If there's anything you didn't understand, then feel free to rewind the video and watch various bits and pieces again. But otherwise, that's all, folks.